Okay, so I'm gonna cover 4.10 force mechanical vibrations. So we're gonna consider the second order linear and then non-homogeneous differential equations. So as you can see that external force is given as a constant f sub 0 and times cosine and gamma t. So this equation model the behavior of object under the force the oscillator forced mechanical oscillators. So here we assume that the gamma, which is the frequency of the external force, and f sub 0 is positive, non-negative, and b square is between 0 and 4 mk. So the b square minus 4mk, which is discriminant of Ox equation associated with homogeneous equation, is as the complex root, right? So we want to find out the solution, general solution of this non-homogeneous non-homogeneous equation. Then using the superposition principle, y of t must be the solution, a general solution to the homogeneous equation plus a particular solution. So we got the y sub h, which is we got y sub h in the 4.9. So since b squared is less than 4mk, so I told you. So in this is the underdamped. So yh must be a times, I mean, the exponential term. So this is exponential damping factor, right? This is the sign factor. And then to find out yp, we gotta use method of undetermined coefficient. Then using the method of undetermined coefficient, the yp, it turns out the yp has that form, okay? So right here, and then the theta, the phase angle theta can be found by this formula. So A1 over A2, right? And this is equal to K minus M gamma squared over B gamma. So now the reason that here A1 and A2 are the A1 and A2 from the undetermined coefficient. So the y, let's just figure out y and yp is like this. So hold on. Okay. So yp basically, since the external force, just to get the type of external force, so f0 times the cosine, right? So yp must be the standard form of the yp particular solution must be like this. So polynomial times exponential term times trigonometric functions. Okay, so here we since the external force, there is no exponential term, so gamma must be 0, right? Alpha must be 0, and then beta must be gamma, and then this is constant, right? So the degree of that this polynomial must be 0, so m must be 0 right here, and n must be 0, okay? And to figure out s, we need to compare the alpha and beta in the complex root of Ox equation with that alpha and beta, right? If they are equal, then s must be 1, otherwise s must be 0, right? So right here, the we know that in the Ox equations, the root the complex root of that Ox equation, alpha plus the beta I here, is equal to minus b over 2m, right? And then plus the square root of 4mk minus b squared over 2m. and I, and then so that alpha here, this is alpha, right? So that's the alpha, I mean the real part, right? The alpha, which is real part, and then this one is the imaginary part, beta, which is okay. So definitely this alpha is not equal to that alpha, and then this imaginary part is not equal to the gamma. So s must be 0. Okay. So now then, thus yp of t is equal to a1, right? A1 and the cosine and a gamma t, right? And then plus the a2. Okay. So here I know, so it should be the b1, right? So but let me just use a1, a2. Okay. So a2. So a2 represent that just b0 actually. Okay. So you can say is a0 b0, then that one must be a0 over b0, right? So a2 and sine the gamma t. Okay. So yp prime then. So then what are you gonna do? We plug in to figure this. These are undetermined coefficient, right? So we substitute yp into the differential equation by finding derivative, the first and second derivative yp. So we put them into the differential equation to figure out a1, a2. So to do that, doing that, then it end up with this k minus m gamma square, the a1, and then plus, and then b gamma, the a2 is equal to f sub 0, and then minus b gamma a1 plus k minus m gamma square, the a2 equals 0. Okay. So yeah, we solve it. We solve the system for a1 and a2. Then it turns out that a1 is equal to f0, and then k minus m gamma square over, and then k minus m gamma square and square plus, and b square gamma square, and a2 is going to be f0, f sub 0, and then b and gamma over k minus m gamma square and square, and a plus, and a b square, and a gamma square. Okay, so now yeah, yp, we figured out yp. Okay, and then let me just simplify yp, because it looks like it seems that yp is so complicated, so we need to factor out something and factor out the common factors and simplify. We need to simplify the yp. So yp is going to be f0 over, okay, so k minus m gamma square and square plus b square and a gamma square times k minus m gamma square, the cosine and the gamma t plus b gamma, the sine gamma t. Okay, here. So now then, cosine plus sine, so we can combine them, right? So now this is equal to, right? So and then so what this is equal to the let's see. So right here, I need to let me just combine these two trigonometric function terms. So considering this one, say this is C1 and this is C2, then we're gonna get combine that, then we got the square root, right? The square root of, this guy, okay? So k minus m gamma squared times cosine and gamma t plus and b gamma sine and a gamma t is equal to the square root, right? And k minus m times gamma square n square plus and then b square and gamma square times sine, right? And gamma t plus the theta. Okay, we can say that. So this is phase angle, this is frequency, and then this is amplitude, right? So we did that. We use so we were used to this technique in 4.9, right? Now see that this is what I mean. Look at the bottom here. Square of this guy is this. So simplifying that fraction with this, then we're gonna get f0 over and a square root, right? The square root k minus m gamma square and a square plus and then b square and gamma square times what? Just sine. The sine and a gamma t plus theta. Okay, so now the tangent here, theta, the phase angle, right? So the phase angle theta is going to be a1 over a2, which is the k minus m gamma square over and b gamma, b times gamma. Right? So and then finally we got we filled out general solution. So the general solution to the non-homogeneous equation representing the motion of this one, the damped, forced, and mechanical vibration. So a times e to d minus b over 2m, right? And then t, and then sine, and square root over 4mk minus b squared over 2m, right? And then plus theta, plus pi. Okay, so that's the this is the solution to homogeneous equation, right? Next one, the plus. Next one gonna be the YP, particular solution to the non-homogeneous equation. F0 over and then square root and then k minus m gamma square and square and the plus and the b square gamma square and sine and a gamma t plus theta. Okay, so that's the particular solution. Okay, so in this case we assume that b squared is less than 4mk. Okay, so now here in this case we keep in mind this b squared is less than 4mk, and here, right, a is a c1 over c2. Okay, arctangent, square root, sorry, this is a tangent, square root of c1 squared plus c2 squared. Okay, so so from here we can observe that so we can observe the first one, the homogeneous solution YH represent the damped oscillation, right? So first one YH, this one represent the damped oscillation. And that depends only on the parameters of the system and the initial condition, right? So look at this YH. So B, M, K, Okay, so these are the parameter, right? So spring constant, damping constant, and mass. So YH only depend on the parameters of the system. And then initial condition A is square root of C1 squared plus C2 squared. The C1 and C2 are just determined by initial condition, right? So we can say that YH represent the diameter oscillation. Yeah, this is under diameter, right? And that depends only on the parameter of the system and initial condition, right? The second one, the limit of e to d minus b over 2mt as t approaches infinity is equal to 0. So which means that we saw that in 4.9, that's damping, exponential damping factor is exponential decrease, which means that YH approaches 0. It means that YH of t, right, approaches 0 as t approaches infinity, right? So which means that as time marching on and on, the solution to the force mechanical vibration will be dominated by YP, particular solution, actually, not this one, right? And then third one, the consequently, YH is referred to as the transient part. So you see, the YH approaches 0, right? So now we can say that YH referred to as the transient part. Okay. All right. So the next observation. So YP is the offspring of the external force, right? So function is. So it's the offspring of the external force, okay? The FEXT. So here FEXT is what? This constant force, initial constant force F0, and then cosine and then gamma t, right? And then 5. Then so YP is a sinusoid, which means the wave, okay, with the angular frequency gamma. So you see that YP is this. So this is the amplitude of this wave, right? I mean, so there is no exponential term or something else like a YH. So this is what why we see the YP is genuinely the wave function, right? So YP is a sinusoid, which means the wave function. So YP is a sinusoid. With angular frequency, okay. The gamma, okay. So now the YP is a transient part. Keep in mind this, okay. This is transient part. And 6, the last one, as the transient part dies off, and the motion YG, I mean general solution, becomes essentially that of the second term YP, okay? That term is called the steady state solution. So as the time is marching on and on, the YH approaches 0, but YP is just still a wave function, right? It's just the B here YP is just the wave, right? So this is a transient part. This is steady state solution. Okay, so let me say that's the transient part or transient term. Okay, so say right here. So YH of t is transient term, and then YP of t is the steady state solution. Okay, All right, so then let me just let me try to visualize YP and YH. What do they look like? Okay, what they look like. I mean, so this is T. Okay, so this is Y. Right? And then YP is gonna be this, right? YP is gonna be wave functions like this. Okay, and then the YH is gonna be this, right? YH is gonna be think probably just for instance, okay. So something like this, right? Because definitely we know that because of the exponential damping factor, the amplitude will be decreased as time goes on, and they combine them. Then I think then they combine them. The general solution gonna be maybe like this. Something like this. So eventually, as you can see that this part. So finally, the general solution. Oops. So this is yg of t. General solution approach what? Approach the yp as t approach infinity. Okay. So that's the we can expect that. Okay. The last observation. So 7. Okay, the factor 1 over 1 over where is 1? Yeah, you see that the ignoring just f0 and then 1 over that square root, this fraction is referred to as the frequency gain or gain factor. Okay, so because that represents the ratio of the magnitude of the sinusoidal response to that of the input force. Okay, so then the frequency this one 1 over the square root of k minus m gamma square and square, and then minus b square and a gamma square. So this is the as the frequency gain. Or a gain factor. Okay. So, and then the gain frequency factor, frequency gain, I mean, this one, let me just say the gain factor, okay? So this gain factor depends on what? The frequency gamma, okay? So, I mean, K and M and B are the properties, I mean, the parameters of the differential equation, right? So K, M, and B are given and then fixed. Okay, so but we're gonna adjust the frequency of external force, the gamma, to figure out the resonance, right? To understand the resonance, right? So we can say that the gain factor depends on the frequency of gamma in the external force. Okay, and then this one represents the what? The ratio of the magnitude of the sinusoidal sinusoidal response to that of the input force. Okay, so please see the example 1 by yourself. Okay, in that example 1, the external force is given by 20 times cosine 4t. So gamma is 4 and the f sub 0 is 20. Okay, so please look at that. So but we want to focus on this one, the gain factor. Okay, so now let me just want to just investigate this one in in more detail. Okay, so let me just say say this is A of gamma. Okay, so in general, the amplitude of steady-state solution. So what gain factor is what? Actually, gain factor is the amplitude of the particular solution, right? The steady-state solution, right? So, and then that's the amplitude of steady solution depends on the angular frequency gamma of the external force, right? So, and then we're going to investigate this one. We're going to investigate that one in detail, and then define this one as a function. So a of gamma is equal to f0, and m times gamma. I just attach the f0, okay, constant in the external force, and then m of gamma, that's the function of gain factor. So 1 over the square root, okay, k minus m gamma square and a square, and then plus b square and a gamma square. Okay, so you know, m, look at this guy, m of gamma. This I told you, but k and b are what, the fixed, right, as the parameter, right? So, and then so we just want to figure out, we want to investigate this one by varying the value of gamma. Okay, so gamma, which is the frequency, right? Angular frequency external force. Okay, so now this m of gamma is called the here, this is a gain factor, right? So right there, but m of gamma actually the by for the various value of gamma, by we can plot the graph of m of gamma, right? So that graph of this one m of gamma, right? This is called the frequency response curve. The frequency response curve. Okay, or just resonance curve. Okay, so let me just describe. I mean, okay, so what does the graph of m of gamma look like? Okay, let's investigate. So to figure out this, you know, I mean, to understand the graph of m of gamma, we'll adopt the calculus. Okay, so we'll try to find out the local maximum minimum where in what interval the function is increasing, decreasing, something like that. So the adopting the calculus technique, so we figure out that. So we need to find out m prime, right? Okay, so because we need to figure out the critical point, right? So m prime gamma going to be minus, and 2m squared and a gamma, okay, and see gamma squared, okay, and then minus k over m, and then minus b squared over 2m squared, okay, and divided by k minus m gamma squared, and a square plus, and a b squared, and a gamma squared, and then 3/2. Okay, so then you know, to find a critical point, setting, you know, m prime equals 0, and then this solution to this equation gonna be what? The gamma, what? If gamma equals 0, right? So what? The solution must satisfy the numerator equals 0, right? Then gamma must be 0, or gamma squared is equal to that, which means that here the solution gonna be 0, or what? Gamma is equal to the square root, right? Okay, square root k over m, right? And then minus b squared over 2m squared. All right. So here, but we drop a negative sign actually. But why? Because we assume that what? Gamma is positive. You see right there. Gamma is non-negative, I mean. So because of that assumption, we drop a negative sign. So yeah, so we are not interested in a trivial solution. It's zero. Okay. So we do interest that. So let me put denote this one gamma sub r. Okay. So in case one, I mean, okay. So but here we have three cases, two cases, right? So this guy is less than zero. I mean, the quantity under the square root is less than zero, or that quantity is a positive. Okay, so we think we just consider two cases each. Okay, case one. So b squared is greater than or equals 4mk. Okay, and then but greater than 2mk. Okay, so what does that mean? So it means that since the b squared is greater than or equals 4mk, which means that this is over damped, right, or critical damped, right? So this means the two cases, over damped and critical damped. Critically damped, sorry. Okay, so that means there is no oscillation behavior, right? And since the then k minus or k over m minus b squared over 2m squared is less than zero, must be less than zero. Why? Because see the the common denominator gonna be 2m squared. This common denominator, I mean. So then k over m gonna be 2mk over 2m squared, right? So, but problem here, the assumption that we suppose that what 2mk is less than what less than 4mk, and the 4mk is less than or equals b squared, which means that b squared is greater than 2mk. So what this is a minus. I mean, so this must be less than, right? And the b squared over 2m squared, right? Because of that. So that's why this quantity is less than zero. Okay. So thus, m prime of gamma equals zero. Only what this is less than zero, but gamma must be what? This is a frequency, must be real value, but we got the complex. So what? M prime gamma equals zero has only one solution, gamma equals zero, right? So this is zero only what? When gamma equals zero. So then since what? The gamma and the gamma I mean the what the original score m of gamma is decreasing function, right? So see that m prime, I mean, so now then give me a second, that is turns out to be less than zero, right? So this is negative, this is negative, right? Okay, and then so give me a second. Okay, now when gamma is less than this value, then there's negative right here, and then there's negative sign, the positive. But eventually, when gamma, the value of gamma is greater than this value, okay, then the gamma squared minus this guy must be a positive. Oh, sorry. So this is negative, right? Negative and negative positive, and the gamma is a positive, right? Gamma squared positive. I'm sorry. So this is always positive, and this is a positive. The negative sign right there. So m prime is always negative. So that's why m of gamma is a decreasing function. Okay. So m of gamma. So since the decreasing function, and then m prime equals zero, I mean, gamma equals 0 is the critical point. So m of gamma approach 0 as what? Gamma approach infinity. Okay. So now then in the m of gamma, m of 0 is equal to 1 over k. Actually, when you plug in 0 into gamma, then we're gonna get the just 1 over the k, right? 0 here, putting 0 in here, then k will be a lot survive. Okay. All right. So now case 2. The b square is less than 2mk, which means that this guy, the quantity on the square root, is positive. Okay, this is underdamped. Okay, so then the gamma sub r is in is positive real value. Okay, and m of gamma. Okay, so the m of gamma has a maximum value at gamma sub r. Gamma sub r. Okay, so substituting gamma r into m of gamma, then let's figure out the maximum value. Okay, that's gonna be 1 over b over the square root and then k over m minus b squared minus 4mk, 4m squared, sorry. Okay, that's the maximum value of m of gamma. All right, and then that's the maximum value. Okay, so then the gamma sub r over 2 pi is called the resonance frequency. Okay. Resonance frequency for the system, and then when the system is stimulated by an external force at this frequency, it is said to be at resonance. So it means that the system will have the resonance when the frequency, the angular frequency of external force has this value, gamma sub r over 2 pi. Okay. So now then let's see. Okay, so now then gamma sub r, but look at this, gamma sub r is what? Actually, gamma sub r has this maximum value, and then this is related to the b. I mean, the damping constant b is involved in this value, right? And gamma sub r has also a b right there. This one is involved the b, right? So I want to figure out the effect of the damping constant b on the resonance curve. So, okay, so yeah, we're gonna get so now to illustrate the effect of the damping constant b on the resonance curve, we consider in which m and k equals 1. Okay, so we set all other the parameters 1 except for b, and then we vary b. Okay, vary the value of b to see how the damping constant b effect on the resonance curve. Okay, so m of gamma, when all value parameters is set to 1, the m of gamma gonna be 1 over square root, and then 1 minus gamma square and a square, and a plus b square and a gamma square. Okay, right here. And the gamma sub r gonna be square root of k over m, right? And the minus in a b square over 2m square. This is equal to square root of 1 minus, right? Because when k and m are 1, this one turns out to be 1 minus in a b square over 2, right? So the resonance frequency then, so Resonant frequency, gamma sub r over 2 pi gonna be 1 over 2 pi times and a square root and the 1 minus b squared over 2, right? So now here, from gamma sub r approach 1 is what? B approach 0, right? 0, right? And then in what? The m of gamma, right? Approach. So think about this. Gamma r approach 1. I mean, B, when B approaches 0, which means that damping force approaches 0, right? Then the gamma r approach 1. If gamma r approach 1, then m of gamma gonna be what? This gonna be gone. This gonna be 1 over b, right? The denominator approaches b, right? Okay. So now then you can say so now this one approach 1 over 1 minus and a gamma square and square as b approach 0, right? And then we know, as I told you, the maximum value will be just infinity, because b approaches 0, the gamma r approaches 0. So what's the maximum value of the m of frequency gain? If frequency gain gonna have the maximum value at gamma is gamma r, but if gamma r approach 1, then 1 minus gamma sub r square approaches 0. So this one approaches infinity. Got it? You got it? So now then then m of gamma r, finally m of gamma r approach what? The infinity as gamma r approach 1 as b approach 0. Okay, so it means so here it basically what? B approach 0 as b approach 0, the maximum magnitude of the frequency gain increase, and the resonance frequency gamma of 2 pi for the damped system approach the omega over 2 pi, which is natural frequency. You got it? So right there, then gamma r over 2 pi, the resonance frequency, gamma r over 2 pi, that's the resonance frequency, right? Frequency approach what? This one, the square root k over, I mean, just say omega over 2 pi. So this is equal, here the omega is natural frequency, the square root of k over m. Okay. Because b approaches 0, the damping force approaches 0, right? So that means what? That frequency approaches what? Natural frequency. So right here, that's the natural frequency. Okay. So now then so that means that means what? It means that gamma r approach natural frequency. Okay. So on damped system, so if damping constant b is very small, so that system approach the undamped system, then the system is subject to large oscillations when the forcing function has a frequency near the resonance frequency for the system. Okay, that's how the resonance happens. I mean with the big oscillations, big amplitude. I mean, okay. So if here's the summary. So if the damping constant, the b is very small, so approach almost 0, Okay. And then the system here, the non-homogeneous system, then is subject to large oscillation. When the forcing function here, the forcing function is f0 and a cosine and a gamma t. Okay, so it has a frequency gamma. So gamma near the resonance frequency. Okay, for the system. Okay, so forcing function has frequency gamma near the resonance frequency, so which means that this guy is approximately, okay, so natural frequency. This is the resonance frequency, and then omega is the natural frequency. Okay, so this is natural frequency. Why did the resonant frequency is approximately, the natural frequency? Because what we assume, we suppose that what b's are very small, because b's are almost zero. Okay, or we can say b is a really small number. Okay, you can say that. Okay, so then resonance frequency approximately equal to natural frequency. Okay, then the system will have large oscillations. P, the amplitude. Okay, so we saw that, right? Goes up, that one goes approach the frequency gain approach infinity. Okay, so that's the here. That's why how the B amplitude of resonance occur. Okay, that's the 4.10. And please look at the graph and the examples in 4.10.